everybody to OpenCV Weekly webinar. And today we have with us Professor Matteo Poggi from the University of Bologna, representing team EyeCan, which is one of the teams that got selected in OpenCV Spatial AI competition, sponsored by Intel. And we are so excited to have you, Professor Matteo, here for explaining what you're doing in this competition, but also illuminating the audience about this new technology called NERF, which has taken the computer vision and AI world by storm. So welcome.
Yeah. Basically, I do my research at the University of Bologna, and I deal with computer vision and deep learning. And most of my works concerns depth estimation, in particular using stereo, for instance. And in the most recent month, I'm giving a look together with the EyeCan boys to these NERF technologies. So we choose this contest also to play a bit with these technologies and try to bring them, let's say, to the real world. Okay.
So before we start the presentation, I just want to also introduce Phil Nelson, who is the content manager at OpenCV.org. Welcome, Phil.
Yeah, good morning, everybody. This is a especially exciting episode for me. As some people know, my first job in the computer vision industry was with Occipital, who made a 3D scanning device based on the old Kinect tech, essentially. And so this is a totally different, style with really exciting results. If this is your first time joining us, or if you just need a reminder, there's a couple of things we do every week here on OpenCV Weekly Webinar, one of which is a special giveaway to one lucky winner in the Zoom audience. Later in that webinar, I will ask a question based on the slides from the webinar, and the first person to answer that will win $200 worth of Azure credits from our sponsors at Microsoft Azure on super fast Intel hardware. Also, we'll be taking Q&A from you in the audience, so please use the little button on the Zoom bar there to ask your question at any point during the webinar, and we'll try to flow it into the conversation, as well as reserve some time at the end for questions we just couldn't get to during the regular presentation.
And one little error on my side, I want to thank our sponsors, Intel and Microsoft Azure, for this competition. In fact, we are running multiple of these things with Intel and Microsoft, and so there's a little bit of confusion sometimes. I'm not sure which one is being sponsored by which. Extremely sorry about that. This competition is being sponsored by Intel and Microsoft Azure.
Yes, use that Oak Delight Contest hashtag to see all the cool stuff that the teams are posting lately. It's been really great to see what people are putting out these days.
All right, let's start the presentation.
Okay, I'm gonna share my screen. Let me know if you can see it. Okay. Okay. So today's talk is entitled ScanNerf, bringing real object into Metaverse. And basically, we will see what we are developing for the contest, in particular, our ScanNerf pipeline that is sketched in this first slide. So let's talk about the Metaverse, what we mean with Metaverse. Basically, since we are hearing about this new concept from a couple of months, and with Metaverse, we mean a tight connection between the real world we see every day and virtual reality or any kind of augmented content we might want to project into our real world. So basically, we can see two main connections between the two worlds, and we will dig further into these connections during this presentation. And on one side, we might want to augment the content we see every day. So we might have some virtual content in the scene we are navigating into, but we could also want to do the opposite. We can bring some real object into a virtual environment where we could navigate, for instance, with this kind of visual we have here. So to give you a taste.
One thing I would like to add about Metaverse is that people may, because Facebook took this initiative with the word Metaverse, people may think that it is only restricted to one company, but the truth is that there will be many metaverses, or whatever the plural is. It is not just one company thing, right? Every company could have its own metaverse. There could be some convergence also, but it is not just one company we are talking about. It is a much more general idea than what Facebook is proposing. I mean, they would have their own metaverse, but there would be other companies that would come up with their own metaverse as well.
Yeah, we could say this will be a way to combine the real universe with virtual reality in any way. And of course, yeah, probably different companies will have different plans for this. So yeah. And just to give you an intuition about one of the two directions we can follow to bring some content from one universe to the other, so from the real world to the virtual world or vice versa. Here we can see an augmented reality application. So in this case, we are projecting this kind of small robots in a scene we are framing with our smartphone. So basically, this scene is a scene from the real world. The robot itself is a virtual object, and we are projecting it into the real world. To do this, basically, we need to do this in a realistic way. We need to model the geometry of the real world, so we can use it to project the virtual object in the real scene and basically make it interact with the scene in a realistic way. For instance, we want this robot to be hidden by this foreground object every time we move the camera and we bring the object in between the camera and the robot. So to do this, we need to have a good modeling of the real world we are observing. Of course, we can also follow the opposite path. We might like to bring a real object, for instance, this kind of tennis ball from the real world into a virtual world in which we navigate, for instance, every time we wear an object like this. So in this specific case, we are projected into a virtual environment where we probably will navigate into castles, forests, and whatever fantastic environment we may imagine of. But maybe we would like to bring some object from the real scene in which we are at the moment we are playing, together with us into the virtual world. And to do this, of course, the mechanism we have to follow is different, because in this case, we want to model for in a realistic way, of course, the geometry and the appearance of this object in order to bring it into the virtual environment and in order to make it interact with the virtual world in a proper manner.
Yeah. Oh, I also wanted to add one more thing about the previous slide. When we talk about computer vision in general, if you move to the previous slide, where you're, so this, adding virtual objects to the real world, it's a very old problem, and we have solved that in many specific instances. For example, when we show the yellow line on a football field, American football field, that yellow line is virtual, and that has been around for more than 20, 30 years. Similarly, having billboards which are virtual in a soccer field, for example, you have virtual billboards where advertisements are being shown. That's also pretty old technology, but there are very specific instances of this kind of technology. When you go to very general, like this one, this is a general thing that you want to put some arbitrary object in an arbitrary scene, the complexity explodes, right? This is 1,000 times more difficult than putting stuff on a billboard in a soccer field. So I just wanted to give that historical context that the idea is not new. The idea has been around for such a long time, but the implementation was not possible because of technical limitations until recently.
It's also true that it seems as though televised sports has pushed a lot of this innovation into the mainstream over the years, I think.
Yep. Sorry for the interruption. Yeah.
No problem. Yeah, that's correct. Basically, this is a quite old-fashioned problem. Yeah, while probably this opposite pathway is something, more recent and for some degrees also more exciting.
Yeah.
So, as I said, we want to model the geometry and appearance of this object the best way we can. And fortunately, we have some very brand new tools that can help us. In particular, since a couple of years, we have this brand new technology that is called Neural Radiance Field that allows to learn, because here we are talking about deep learning, to learn the geometry and appearance of an object, or in a more complex scenario of an entire scene, by simply training a neural network on a very specific object or scene, in order to use this neural network itself, once it is trained, to build a geometric model of the object itself, or to render images from the model itself. So basically, this is quite a different paradigm compared to what we are used to know from deep learning, because usually we train a neural network and we want this neural network to generalize to any possible scenario we can encounter. In this case, the neural network is, I would say, overfitted on a single object and a single scene in order to be able to reproduce this scene or object, for instance, from a different point of view. And to do this, this network is very special, because the input to this network are the 3D points in space we want to reproduce in our 3D model, or in our in the geometry of our scene. And the neural network is trained given the 3D coordinates of any 3D point in the scene. It is trained to produce a density and a color for such a point in the 3D world that we can use either to build, for instance, a 3D model like the one we can see here, or to run some kind of rendering of the 3D model, and to retrieve basically some 2D images from a single point of view that we can select at any time after training. So, like I said, this is an approach that is quite new in computer vision, because basically most of the time we are used to do the opposite. We have images and we want to recover the geometry from the images. Here we want to build, I would say, a compact representation of an entire scene, and we want to use this compact representation to observe the scene from any new viewpoint we want, to obtain even new images or images that we have already observed. So this kind of,
Can I just add a little bit to what you just said, so that we are, I'm playing the role of our audience, so that I'll keep summarizing what you just said, because this is so important. And
it's so much different too than like it's not necessarily obvious, because it's so different than the like kind of standard way of doing like a 3D scan. This is much more of capturing everything, including the scene that it's in as well. Go ahead, Satya.
Yeah. So, I mean, the way I look at it is that, think about this NERF, this new kind of neural network, as a black box, right? Don't worry about anything else. It's a black box. And the input to this are various pictures of the scene. So you move the camera around, take several pictures of the scene. Maybe you take a picture by moving the camera in a circle, but the idea is that you take the picture from, let's say, a dome or other places, as many pictures as possible of the scene, and you feed it. That's the input to the neural network. You train the neural network, and this black box gets trained. Now, during the inference process, what you want is, given any viewing direction, right? So you threw away all the input images. We are not interested in that. The only thing you have right now is this trained neural network. The input to this trained neural network would be a viewing direction. You would say that, oh, I want to look at the scene from this viewing direction, and it would output an image of the scene from that viewing direction, from that novel viewing direction. You may not have any image from that particular viewing direction, looking into the scene. But this trained neural network is such that it will produce the image for you, even though you may or may not know the geometry of the scene, right? Is that a fair summary, Matteo?
Yeah, I would say this kind of resume everything. Yeah, we can see this neural network as, I would say, a digest of the scene. So,
right. Okay. So it is representing the scene in these weights instead of pixels, right? Yeah. Okay.
Yeah. Thanks for resuming. Also because this is quite hard to explain in a few minutes. So yeah.
Right.
So yeah, basically, what we can see here in this video are what we might think they are 3D objects rotated in space. So here we can see this kind of chair rotating around. We might think we are rotating this chair around, but basically this is exactly the effect of what Satya said, because here we are simply rendering, so we are generating images from this kind of chair from different viewpoints in space. So basically we can get an image of this object from everywhere around the object itself. And to obtain this kind of effect, of course, we need several images that we want to collect from all around the object. The more images we have, the more precise and accurate the neural network we will train will be. So we collect these 100 images and we use them for training. Once we have trained our neural network, we don't need these images anymore. And we simply ask the neural network, given a single point of view, to generate for us the image we want. And yeah, as I said, we need to collect several images all around the objects. So the basic assumption is that we take our camera and we move around the object. Of course, we can simulate the very same behavior if we do not move around the object, but if we move the object itself. So to obtain something like what we have seen in this video.
Quick note here. I was joking with a friend of mine that we should have a drinking game on this show, that every time we see a camera frustrum, I think that last slide would have killed both of us.
Yeah. And
what about yourself, Phil? Okay, go ahead.
So yeah, basically what we observe in this video gives us an intuition about this. Here we don't really know if we are rotating the object itself or if we are moving the camera around the object. So what we want to do is to obtain this kind of effect. We want to collect all these hundreds of images of the object itself, yet we want to optimize this acquisition process. So yeah, we can move the camera around to some degrees, but maybe we cannot reach any corner of the scene. And we can compensate for this missing information by simply rotating the object. In order to do this, we will see that we can implement an hardware platform for this. And if we are able to collect these 100 or even 1,000 images for a single object, we will see that we can obtain a compact representation, a compact model of this object that we can use to render any kind of image we want, and so basically to have this object projected into a real world. Because once we are capable of rendering this object from any possible viewpoint we want to frame it, basically this is what we can do once we are in the real world and once we want to render this kind of object for any kind of actions we want to play in the virtual world. So basically, once we have done this, we can simply bring our object to the metaverse. So to implement this kind of process, we have built what we call a scan station. This kind of scan station basically allows to collect images according to 2 different degrees of freedom, because we have this kind of arm over which we can mount our camera to scan the object, and we can move the arm around to modify the height, for instance, at which we collect the images. Of course, moving the arm this way somehow limits the amount of viewpoints we can collect for the object itself. However, if we design this kind of table over which we can put the objects during scanning, and if we design this table to be capable of rotating, we can simply collect images all around the object in 360 degrees, for instance. And thus, combining this kind of rotation of the table together with the rotation of the arm itself, we can really acquire thousands of images from a very different point of view of the object, and thus obtain a higher density of images that we will see can allow us to train the network at the best. Once the network is trained, of course, we will be able to reproduce the object we have scanned from any different viewpoint and obtain, of course, our virtual twin of the object. So this is simply a concept of the scan station itself. Let's have a look at the very first implementation we built of our station. Here we can see on the left the basis of the arm we are rotating around the scan station. We will have a larger picture of this in the next slides. And we can see that during the acquisition, the camera moves from top of the scene down to the basis, while the table itself rotates, allowing us to collect images from any viewpoint of these Lego blocks we have on the rotating table.
And importantly, it's also every viewpoint will have different reflections and stuff like that, which matters a lot here.
Yeah, we will see this point about reflection is one of the main challenges in this kind of process. Finally, before going to the next slide, we can see we have a chessboard on the rotating table, and we will see in a while that this chessboard is required to recover the information about the viewpoint of the object itself, and we will use this information during training, because of course, once we train the network, we also need to tell the neural network every time we give an image to the network itself, we need to tell which is the viewpoint that is used to acquire the images, in order to allow the network to, of course, learn the entire geometry of the scene. So this is, let's say, a picture in large of the ScanNerf station that we are building for the challenge. Basically, we have the arm over which we mount our OCD light camera that we use to collect any image of the object we want to scan. Here we have our table over which we can put the chessboard that we use to estimate the viewpoint, as well as the object we want to scan just on top of the chessboard. And finally, we use 3 motors. A couple of them is used to basically rotate the main arm of the scan station. And the third one is used to implement the rotating table, allowing to get different viewpoints of the same object while rotating. So basically the entire scan station, as we have seen in the previous video, and as we will see in the next videos, because I will show you a couple of examples of acquisition of objects. Basically the arms fixes its height over the scene. We rotated the table a couple of times in order to be able to collect multiple images of the same viewpoint. Then once we have rotated the table a couple of times, we tilt the arm in order to move it toward the basis of the scan station. Once we have moved the arm, we repeat the rotation of the table, so we collect another set of images, then we move the arm again until we get to the basis of the station. With this process, we will see we can collect about, I will tell, more than 5,000 frames that we can use, of course, to train the network itself and basically to model our object and to bring it to the virtual reality. So in this slide, I just show an intuition about the different viewpoints where the camera collects the images during the scanning process. So we can see here on top, we have the very first round, the very first cycle of acquisition from the very top view of the scene. Then we have this inner cycle that corresponds to the first movement of the arm. So we first move the arm and then we rotate the table a couple of times. Then we move again, again, and again until we reach the lower bound of the scanning station. And as I said, this results in more than 5,000 images. Of course, we could even augment this amount of images by simply moving the arm with smaller steps between one cycle and another. So here I show you a couple of pictures of what the OCD Lite camera sees at the very beginning of the acquisition process. So here we have the color image acquired by the center camera, and here we also have the grayscale images we can collect with the left and right side cameras. Everything we do in terms of data collection and neural network training is done on the color image, because we want to effectively learn a color representation of the object itself, while we can use, and we will use in the following steps in the challenge, we can use the stereo pair itself to get some depth information about the scene and to do some further post-processing, because knowing in advance the geometry of the scene can help both the neural network during training, or can help us to segment the object itself for the scene, because we will see in a while that we need to take into account that we are not only moving the object itself, but we are also moving the table and the background with respect to the movement we do with the camera. Because one of the basic assumptions of what we do when we train a neural radiance field is that we observe a static scene and we move the camera around. In the pipeline we have sketched so far, okay, we are moving the camera, but to compensate for some missing viewpoints about the object, we are also moving the scene. So we are violating the basic assumption behind neural radiance fields. So if there's any question or...
I can do one actually. So we talked a bit about the reflections. Par Ando would like to know, as a result of this, can you render new images with different lighting conditions?
Well, you can if you somehow model this kind of different illumination source. In our project, actually, we are not focusing on relighting or modeling this kind of illumination. So to reduce the reflection to be the minimum, we basically collect all the images in a white room, and for now we are experimenting with objects with minimal reflections. But of course this is something that should be taken into account, in particular because if we move the object itself, we will basically see different reflections on the object, and so again we are somehow violating the basic assumption that the world is static and the camera is moving. So for now we are limiting the reflection at the most. But yeah, this is something that should be modeled.
Yeah, and I think in terms of making things feel much more real when you bring them into these virtual spaces, the reflections are a huge part of that. It's as important as attenuation for audio or reverb, where nobody really sounds like they're near you or far away from you unless you've really accurately modeled those, because our minds, our brains are so tuned to the way our ears hear stuff and the way our eyes see things in real life that When you bring stuff into the virtual spaces, and maybe they don't cast realistic shadows, or maybe the reflections are all off based on the scene, it really takes you out of it. It's much less real feeling, I think.
For people interested in relighting, etc., they can look at this paper called BlockNerf, I think, where street view images were used, and they are taken with different at different times of the day, etc. And so, they are able to generate not only what the scene looks like from different views, but also different times of the day.
Yes, Niraj posted that in the chat about 10 minutes ago. Way ahead of us. Thanks, Niraj.
Okay.
Okay, so once our pipeline has been sketched, we started scanning different objects and basically bringing them to the metaverse. So here I'm showing you an example of an apple we are scanning, and I will catch your attention on a few details. For instance, once we move the arm, we can observe some vibration of the camera. So we will need to deal with this, and we will see in a couple of minutes how to deal with this. And again, I would like to point out the attention of on the chessboard, because the chessboard is necessary to estimate the viewpoints at which we are collecting the images. And this kind of chessboard is not a standard chessboard, is a Charuko chessboard that has some peculiarities. And without going too much in details, the good point about this pattern is that it is very robust to occlusions. And as you can see here, we have plenty of occlusions. So if we use a standard chessboard, probably many times we would not be able to estimate the viewpoints, while with this kind of pattern, we can always estimate the correct viewpoint, and then we can estimate it for any of the 5,000 images we are collecting. So as you can notice, the object itself from start to the end changes its appearance a lot, because basically we are collecting it from many viewpoints. And this allows us to obtain as a final result this kind of model. So basically here we are observing in an interactive way the apple we have scanned so far. And to do this, in this specific case, we are using a neural radiance field. In particular, I would say very recent and advanced evolution of the neural radiance field that is called instant neural graphic primitives, that basically makes the entire process faster. And as we can see, we can interact with the object, we can rotate it, we can inspect the object itself from any viewpoint, and the final effect is very realistic. So a few more details about what we do during the scanning process. As I said, from the video, we can easily notice that the camera itself vibrates a lot once we move the arm. But we can easily find this behavior from the Charuko chessboard itself, because when we estimate the viewpoint for this kind of acquisitions, we can see that the z-axis, of course, changes a lot during the acquisition, because the camera itself is moving a lot. Mm-hmm. So we can find these, I would say, orange patterns, and we can simply filter out any image collected during this kind of fluctuations. Mm-hmm. This way, we can ensure that we are taking images that are not blurred because of the camera motion, and so we can use them at the best to train our neural radiance field. Finally, another important detail about our scanning station. As we have seen so far, we are moving both the camera and the object all around, so we are violating the basic assumption behind the neural radiance field. But we can overcome this problem if we only focus on the object itself, because the main component in the scene that is violating the assumption is the background that is moving together with the camera itself but it's also moving with the object when we rotate the table. So we simply need to get rid of the background, and to do this, we can simply compute some kind of mask to be applied to the scene itself. For this specific case, and in most cases, we can simply look at the color in the image, because we can see here the apple itself is the only colored object inside the chessboard. So we can simply look, for instance, at the variance of the color channels that will be very low where the pattern is black and white, and will be much higher for the object itself. Of course, this is good if we are scanning a colored object. If we are scanning a black and white object, this won't work, but we can reason about some priors. For instance, we know the chessboard is a plane, and we can use the OCD light camera also to have some depth estimation of the apple itself. And we can basically segment the object into the 3D space and remove everything else that is not part of the main object. So just to give you a quick example about the segmentation process, here is another scene that we are scanning. Here we are scanning this toy. This is the mask we can obtain through color analysis and depth analysis. And this is the final image we obtain if we mask everything around the object with an alpha channel. So we can obtain thousands of images of this single object, and then we can start training our neural network, in particular, in this case, our instant neural network. And we can see that after a few seconds, our object has been rendered, and we can interactively render the object itself from different viewpoints. So basically, we have modeled the object itself in 3D space, and we are ready to bring this into any kind of virtual reality application we can imagine. I have another example here. I'm showing the rendering process slightly slowly. This toy is, a different toy. Here we have taken a taxi car, and we can see that after a few seconds, during which the neural network learns how to model the object, after these very few seconds, then we can interact with the 3D space, and we can render images from any viewpoint of the single object.
That's amazing. 4 or 5 seconds of training?
Yeah, it's just a matter of seconds, yeah. Also, wow. Of course, the resolution of the image itself has an impact on this, yeah. But with the OCD camera, just using, I would say 1K images, we can train the network in seconds.
Is the training also happening on the OCD light?
No, not yet. Not yet.
Yeah, that would be quite.
Yeah, that would be, I would say, astonishing. Yeah, no, here, of course, we need a GPU. So, and of course, the training is also
for now, anyway.
Yeah, for now. And of course, the training is that fast because we have thousands of images. We have thousands of images. If we would have, I would say, just 10 images or maximum 100 images, the process itself would be slightly slower, and probably we will not be able to render the object from any viewpoint. But the good point is that the scanning station allows in, I would say, 10 minutes to get all these 1,000 images, and then to train in a matter of seconds this kind of representation that basically is what is all we need to bring the object into the virtual world.
Wow.
So just to sum up, I'm showing you a couple of pictures about objects we are scanning just in these couple of days. We have taken, a lot of toys because they are easy to place on the scanning station. And here I'm showing you a couple of screenshots, both from the viewpoint of the OCD camera. So here, this is what, on top, this is what the camera is acquiring from the scene. While on the bottom row, we have an external camera that has been synchronized with the OpenCV camera, just to show to the audience and to ourselves what we are doing with the scanning station. So we start from the very top, and then we move the arm. Of course, between one movement and the another, we are rotating the table. And in the end, we reach the very bottom of the scanning station. So that's all about what we are doing for the challenge. And basically, this is the standpoint at which we are now. And yeah, before concluding the talk, I would like to thank all the attendees, but also all the guys that are behind this project, that are Daniele, that is the CEO of EyeCan, but also all the other guys that are working together with us, both in terms of theory and also in terms of practice. We have a lot of discussions about how to use this neural radiance field to get some real application and possibly something that we can use off the shelf in a new environment. So thanks to Luca, Federico, Damiano, Marco, and Nicola.
That's great. That's a great presentation.
Thank you.
So, yeah,
thanks.
We can,
that was great.
We can, because we just in time, we have very good on time. We have time for a lot of questions.
Yeah, definitely. Yeah, well, let's go ahead and do our trivia giveaway first. So today, go ahead and unshare your screen, please.
Yeah.
Thank you. Thanks. Yeah, that was great. Thanks for that excellent presentation. So it's time for our giveaway. We'll be giving away $200 worth of credits to Microsoft Azure on blazing fast Intel hardware, thanks to our sponsors of OpenCV Spatial AI Contest. What's going to happen is you in the Zoom chat are going to answer the question I ask in the Zoom chat. The first person to answer it correctly will win $200 of Azure credits. During the presentation, we noticed that there's a specific kind of chessboard that they use when they're scanning these objects. What is that style of chessboard called? There we go. All right, looks like Silverio got the answer correctly first. It is Charuko. It's a combination of chessboards and Aruko markers. So congratulations, Silverio. Silverio. Please send an email to phil@opencv.org, and we'll make sure that you get your Azure credits.
That's great. And just we tell people about resources also. If you can actually print these things at your own home, print it correctly, and use for your own applications, for calibration applications. And OpenCV has all the right tools for helping you calibrate your cameras using Charuko markers as well. But if you want to if you're looking for something industrial, you could go and check out calib.io. They have these patterns on very nicely printed board, etc. And they are not a sponsor or anything. I just thought that it's a good resource people should know about. Maybe next time we should get them as sponsors.
Yeah, but, and they're boards, like thick enough, because one of the important things here is that it has to be very flat.
Yes.
That it materially affects the quality of the calibration hugely if it's not super flat. And so
yeah. So yeah, for people who are looking for that kind of calibration, industrial grade calibration, they should look at calib.io.
Definitely. So yeah, let's get to some questions. Some really good questions here. Your presentation sparked a lot of people's imaginations. Bob and Dan would like to know, how did you scan the bottom of the apple?
Yeah, that's a good point. Actually, when we have seen the video about the apple, there was some kind of illusion, because actually the apple had an hole at the bottom. We didn't figure out because we could see, I would say, the inner part of the apple that is of the same color of the apple itself. And so we were tricked about this. But of course, right now, the apple itself does not have the bottom. So okay. This is something we are looking into, because we had a couple of ideas about how to fill the object all around. But yeah, right now we cannot see just from the bottom of the chessboard. Yeah.
Yeah, in the past, I've seen people, like hanging objects with like fishing wire or like a very thin filament, so they can move the camera underneath as well. Um,
I've
yeah,
also
so it
seen
was just an optical
scanning.
illusion, is what you're saying.
I have also seen commercial scanning applications where they literally asked you to invert the object. So they do one scan and then they ask you to invert the object and put it, and some way they were able to fix, find the correspondences, etc. So that's another option. Not trivial. It's actually very tricky to do that, but I'm pretty certain I have seen this. Even 10 years back. My memory is a little bit shaky, but I'm almost certain that I have seen this.
Yeah, somebody also suggested, what about a glass board? It's not the worst idea, but
we were thinking about something about this. If we could just get the viewpoints without using the chessboard, we could just use a glass. But we need to take care about the glass because probably the light passing through the glass could have some kind of, I would say, effect on the final rendering. So I'm not sure. Of course, this is something that we should study, but I'm not sure it should be so straightforward, let's say.
yeah, definitely an interesting problem. The results, I mean, are really cool. I love I really liked seeing the external image of the rig there, because I was wondering myself, like, how are they actually tilting it like that without it like falling over. I'm also imagining, part of the spirit of this competition, OpenCV Spatial AI Contest, is we're prototyping things with Legos that we could then scale up, to industrial size. And I'm imagining how cool it would look with this giant, rig maybe made of like wood or metal that you could scan like a person sized or like an actual, like a full sized car with. Be pretty cool. Let's see, more questions here. So Local would like to know, will we be making the source code available for this project?
Yeah, actually, I can't tell about this because, Daniele should be the right person about for this question. So, yeah.
All right,
So,
we'll follow up with
I don't
team
know.
leader.
I don't know. Yeah.
Yeah, I mean, you are representing the university, and Daniela is the CEO of EyeCan, and they, technically, EyeCan is the team. EyeCan is the competitor in this one, and it's a collaboration between university and industry, and they will. It would be great if they do it, but it's not a requirement of the competition.
He says in the chat, next year we'll scan a real dinosaur. Thanks for that. Richard would like to know, are there limitations regarding the input image resolution?
Okay, yeah, that's a good question because for some kind of neural radiance fields frameworks, this represents a limitation because, of course, the higher the resolution, the higher the memory requirements during training. And before using this kind of instant rendering tool, we tried a couple more, and some of them had some kind of limitation in terms of memory. Basically, just using for training something like 1,000 images at 1K resolution was just too much for some tools. For this kind of instant tool, this is not a problem. I guess we can scale up to this kind of 5,000 images, maybe getting to higher and higher amount of images. And of course, resolution at some point could be an issue. Yeah.
Yeah, that makes sense. Richard would like to know, can this handle objects with transparent or semi-transparent surfaces?
Yeah, that's a great question. And right now I would say no, because right now, I would say the vanilla neural radiance field would have many problems with transparent objects. In particular, I think there's a couple of following up papers showing some results with transparent objects, and you could see that the 3D models that the network learns basically do not have the, I would say, the 3D surface in correspondence of the transparent object. Maybe you can get some realistic rendering because the network itself learns to propagate the color through the space. But I would say you would have some problem in case of 3D modeling, and at some point maybe you can get this issue out once you render from some specific viewpoints. So I would say this is an open problem, but yeah, of course this is a challenge. Yeah.
Yeah, that makes sense. And that's, historically, that's been one of the toughest problems with 3D capture of any kind is the reflections, but also translucency and fully transparent, like glasses, for example. I remember back in the occipital days, if we did a 3D scan of somebody's head, it would just not, lasers see through glass. And so it would basically look like you were wearing a mask, like a raccoon mask when you were wearing your glasses. Tim would like to know what file formats can this be exported to, like some format to directly bring into a Metaverse project or like an Unreal Engine scene or Unity?
Well, yeah, this is something we are working on because actually once we have this kind of representation, we can simply extract the object itself from the neural network, and we can render either a mesh, either a point cloud, whatever you want. So right now we are still studying which could be the best option to bring everything there. Also, another maybe very challenging opportunity could be to have the several aspects of the environment encoded by single specific neural networks. So have a further different representation that could interact one with the other. Of course, maybe this is looking a little far into the horizon, but I believe at some point we will get something like this. Yeah.
I have a follow-up question. Do you know of any initiative with, Unity or Unreal Engine where they are trying to render nerves directly without having to export? Because, you can imagine that some of the nerves would not capture the 3D geometry appropriately, but still render it just fine. The rendering may just look fine. Is there any work going on in that area? Are people doing it?
Actually, I'm not aware of any, but okay. I think at some point they will consider this because the potential of this kind of instant neural radiance field is huge. So.
Yeah.
Yeah, and as more and more devices have onboard dedicated AI processors that are even separate from the GPUs, like on modern Apple hardware and certain other systems, I think it becomes more feasible to do that in really high resolution virtual spaces as well. Like right now, it might be a little too computationally expensive to be rendering the nerfs in the current state while there's all this other stuff going on with different light sources and different people and being tracked and all that kind of stuff. Yeah. John would like to know, what is the size of the trained rendering model, say, for example, with the Apple object?
Okay, yeah. I would say this depends with the specific neural radiance field implementation you use. For instance, the very vanilla implementation simply saves the object itself encoded into a neural network. So the size will be a few kilobytes. While more modern approaches pursuing speed, both in terms of training and rendering, also use additional representations, such as, for instance, voxel grids and whatever. And this most of the time comes at the cost of memory. So some of these frameworks saves up to, I would say, 600 to 700 megabytes of data. So yeah, you get the speed, but you pay for the memory. So
right.
Yeah, and that's not a huge amount, but it's still it would make it difficult to do it on board certain devices that don't necessarily have that much available. Yeah, that makes sense.
I would say it depends with the application, because of course maybe you cannot store 1 GB of data, but you can store maybe the images at a high enough resolution, and then you can instantly render the model from the images. So maybe this is something you can do. Maybe in some application you can, maybe in some others you cannot. So I think this kind of trade-off is just at the very beginning, and we should study a lot what we can get, what we can gain on one dimension if we pay on another one. Yeah.
Yeah, those trade-offs are, that's how things get, specialized to be built in, specific fields and specific use cases, is those figuring out what those trade-offs are. And so, yeah, definitely. It's very exciting, because I mean, this method is really, how old? This is only a couple of months since this paper came out, isn't it?
Yeah, this one about the instant radiance field, yeah, it's just a couple of months. Yeah.
Yeah, looking
maybe
at
less,
yeah, it says January. It came out in January, so I mean, very, very state of the art. Yeah, let's.
So
go ahead.
Can I just plug in a few things before people leave?
I was just about to suggest that.
Okay, our Kickstarter campaign for deep learning with TensorFlow and Keras course is running right now, and we just added OAK-D Lite to the campaign. It is as an add-on, so you won't see it until you back the campaign, but we have allowed people to back the campaign with just $1 pledge to be able to get OAK-D Lite. And during this campaign, OAK-D Lite, not during this entire campaign, but until we run out of supplies, OAK-D Lite is being sold at $99 with the $1 pledge. So let's say $100. So you can go and check it out on our Kickstarter campaign. One thing I want people to know very clearly, that there, the shipping cost could be very high. So you should look at our update where we give a shipping calculator. And also, depending on the country where it is being shipped, there could be additional charges for customs, duties, etc. So this $99 is just the cost from our side. You need to add shipping cost and customs cost, etc., which can be pretty big. Unfortunately, I missed mentioning this point in my last email that was sent out. Apologies for that. I mean, we'll reiterate this point in our next email newsletter. But in our update, we have clearly mentioned this point. But OAK-D Lite still, even with all these things, and especially for people in the United States, it's a very good deal, because OAK-D Lite is selling at $149 just for this campaign. We have brought the price down to $99. And after we run out of the $99 thing, it will be raised to $109. And finally, it will settle down to $119. So check it out if you're interested in this. And also the campaign, if you're interested in deep learning with TensorFlow and Keras, this is one of the, we'll make it one of the best courses online. And as part of this, backing this campaign, you will also get a chance, you will get a copy of Deep Learning with Python course, a Deep Learning with Python book by Francois Chollet. So yeah, check out.
And it's a big old book. I mean, it's you could choke a horse with that thing.
Yeah, right there. That's the book. So and the second thing is that we are also going to do another interesting competition. It's called the AI Show. The first pilot will be done in about a month or so. And for that, we will bring in some guests and we will ask them questions about AI, but not necessarily deeply technical questions, right? I mean, it will be somewhat technical, somewhat interesting. And if you have any questions that you find interesting, some AI question, some obscure fact about AI that would be interesting to ask in the competition, in the show, please send us your suggestions. You can send us your suggestions at newsletter@opencv.org. And we'll acknowledge, we already have a list of questions. And if your question is new and we use it, we will definitely acknowledge your contribution in the credits.
Yes, the OpenCV AI game show is really exciting. You can sign up to be the first to learn more about it at opencv.org/game show, all one word. Yeah, we're still in production here. It's going to be really great. We've got an awesome host. We've got some really exciting contestants that we'll be revealing over the next couple of weeks. So stay tuned for that for sure. Anything else? You want to take us home, Satya?
No, that is it. Thank you so much, Matteo, for this exciting presentation. We learned a lot, and I'm sure that our audience learned a lot as well. And thank you for participating in this competition. We are very excited about your submission. Finally, when it happens, it's really all exciting stuff. And thanks, Phil, for organizing this this webinar. And finally, thank you all the people around the world who come here and encourage us to do this webinar every week. Thank you so much.
Yeah, thanks everybody. Next week's guest will be another OpenCV AI contest team, so stay tuned for that. We'll see you next Thursday, 9 a.m. sharp.
Yeah, and a final shout out to our sponsors, Intel and Microsoft Azure, for making this competition possible. Thanks.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by Intel and Microsoft Azure as part of OpenCV Spatial AI Contest. Follow along with the OakDLight Contest hashtag. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.